Recall from the previous video that to compute the derivative of a function composition, we have to use the chain rule. So here's the statement of the chain rule. We can say we have a function composition h of x defined as f of g of x. And then the chain rule tells us the derivative of that is f prime evaluated at g of x, then multiplied by g prime of x. And I'll post a link at the top to the video where that was first derived. Now in that video, we worked one example of a chain rule derivative, and it turned out to be really cumbersome because we were explicitly identifying the f and g in that function composition, and then finding the derivatives of those, and then putting everything together. So I'm going to call that the hard way to apply the chain rule, and we'll apply it to this example in just a moment. But first I want to promise you there's an easier way to apply the chain rule. So we're going to develop an efficient, intuitive method for computing chain rule derivatives. And this is the way physicists and engineers, in other words, people who use calculus, think about the chain rule intuitively. So let's get through this the hard way first. I have a function composition h of x equals cosine of 3x minus 2. And to use the chain rule, I need to explicitly identify what the f and the g are in this function composition, and then I can apply the formula. So the f is going to be our outermost function here, and that's just the cosine function. So f of x is cosine of x. The g is our inner function, which is 3x minus 2. And then we can just verify real quick that the composition of these two functions actually gives us the original function h. So if I calculate f of g of x, that means we're getting f of 3x minus 2, which means I take the formula for f and I replace the x with a 3x minus 2, and that gives us the cosine of 3x minus 2. So we've correctly identified the f and g. So now we want to get the derivatives of f and g. So f prime of x, that's the derivative of the cosine function. That's the negative of the sine function. And g prime of x, that's the derivative of 3x minus 2, which is just 3. So now we can apply our chain rule formula. I'm trying to find h prime, and that's f prime of g of x multiplied by g prime of x. So I need to take my formula for f prime of x and evaluate it at g of x. So that's negative sine, and then replacing the x with a 3x minus 2, I get negative sine 3x minus 2. And then I multiply by g prime of x, which was a 3. And we can say this a little bit nicer. I'm going to write it as negative 3 sine of 3x minus 2, and we've got our derivative. But there's a way more effective way to think about the chain rule, especially when we start to get into more complicated examples. So I'm going to phrase it this way. Suppose we're dealing with some function u of x, but we can view that as a function composition, so a u of v of x. In other words, we recognize there's an outer function and an inner function. Then the Liebniz notation gives us a really nice mnemonic device for remembering what to do. And this is typically what a physicist would present to you as a quote-unquote proof of the chain rule, but really we should view it as more of a mnemonic device for remembering how the chain rule works. So on the left-hand side here, I have a du dx, the derivative of my total function with respect to x. And what I'm showing here is that it can be split into a product of two different derivatives. In the first one, I differentiate my entire function with respect to v. So I'm taking a derivative with respect to the inner function, treating the inner function as the variable for the moment. Then we have to multiply by the derivative of that inner function with respect to x. So that's our revised version of the chain rule, and I don't expect you to really understand it until you see it put into practice a few times. So let's go back and work that original example with this new approach in mind. So I have this function cosine of 3x minus 2. Clearly the outer function is cosine and the inner function is a 3x minus 2. Now what this new representation of the chain rule is saying is take the derivative of the outer function with respect to the inner function. So we start with that. I'm going to differentiate the cosine function with respect to 3x minus 2. Now that means just treating the 3x minus 2 like it's a single variable for the moment. So I treat the 3x minus 2 like it's just a single variable, and the derivative of cosine is negative sine of that variable. So that's the first step in the chain rule, and then I need to tack on the derivative of that inner function with respect to x. So the derivative of 3x minus 2 is just 3, and I tack that on. And I'll move the 3 out in front just to be polite, and I get a negative 3 sine 3x minus 2, and we're done. So already we're seeing this is far more efficient. And with a little bit of practice, it becomes just totally intuitive and reliable. It's just a better way to compute chain rule derivatives. So next, we're going to solidify this process with a couple more basic examples. And then at the end, we'll look at an example of a function of a function of a function. In other words, a triply nested function composition, and we'll see how this basic approach to the chain rule extends to that case. So in our first example, we have the function 5 minus 4x all raised to the 10th power. Now clearly 5 minus 4x is the inner function here. So to find the derivative of this function, we differentiate with respect to the interior function, treating it like it's a single variable for the moment. And the derivative of a variable to the 10th power is just 10 times that variable to the 9th power. So that's just the power rule. And then the chain rule says we have to tack on the derivative of the interior function, which is a negative 4 in this case. And we'll combine the constants out in front, and we get negative 40 times 5 minus 4x to the 9th, and we're done. The next example combines the product rule and the chain rule. So we have a product here of two functions, 2x out in front, and then the second function is sine x squared. Well, that second function is a function composition, with the sine function being the outer function and x squared being the inner function. So we apply the product rule here, and in our first term, we take the derivative of the first function. The derivative of 2x is just 2, and we leave the second function alone. So 2 times sine of x squared. Now we add to that a second term where we leave the first function alone, so that's 2x. And then we have to get the derivative of sine x squared, which again is a function composition. So we start by differentiating with respect to x squared, treating that like a single variable just for the moment. And the derivative of the sine of a variable is just the cosine of that variable. So I get a cosine x squared. Then I have to tack on the derivative of the interior function, and the derivative of x squared is just another 2x. So cleaning things up a little bit here, there's nothing we can really do with the 2 sine x squared. But in my second term, if I move those two x's together, I get a 4x squared cosine x squared, and we're done. Now in our final example, we have a function of a function of a function. So the outermost function is just raising this thing to the 5th power. Inside the parentheses, we have a 2 sine x squared minus 1 plus 3. And that x squared minus 1 piece, that's the innermost function of this triply nested function. And the main point I want to make with this example is that you don't have to do everything at once. So we can really take our time here and actually do 2 different steps where we take derivatives. So to start things out, I'm going to differentiate with respect to the interior function, where I'm just treating that whole thing as the interior function. So I just have a variable expression raised to the 5th power. And at this first step, I'm just going to get 5 times that variable to the 4th power. Now the chain rule says we have to tack on the derivative of the interior function. And you don't have to actually compute that derivative right now. It can be really helpful to just put in a placeholder step. So the chain rule says I have to tack on the derivative of that guy. I'm just going to leave a prime on it in this step, and I'll compute its derivative in the next step. Now because this was a triply nested function, that next derivative is going to require another application of the chain rule. So this part out in front is a spectator, 5 times 2 sine x squared minus 1 plus 3 to the 4th power. And now I need the derivative of 2 sine x squared minus 1 plus 3. Now when I take the derivative of that, the derivative of 3 is just 0, so I'm not concerned with that piece. And I get a 2 times the derivative of sine x squared minus 1. Again, that's a function composition. So I take the naive derivative where I treat that interior function as a single variable, and I just get the cosine of that thing. And then I have to tack on the derivative of the interior function, which is a 2x. And again, we're going to try to clean this thing up decently. I have a 5 and a 2 and a 2. Those all multiply to 20. And I have an x that I should bring out in front, so I have a 20x. And then I'll bring out this cosine piece in front. So cosine x squared minus 1. And finally, the 2 sine x squared minus 1 plus 3 all raised to the 4th power. And we're done with that one. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left. Or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.